Thevenin's theorem, it states that any active linear network with output terminals A and B can be replaced by a single voltage source, let's call it as Vt, in series with a single impedance Zt. So we have a linear active network with two terminals A and B. So this is a linear active network. So the theorem states that this can be represented by or is equivalent to a single voltage source Vt in series with a single impedance Zt connected across the two terminals A and B. Right? So let's take a few problems and let us see how we can apply Thevenin's theorem and obtain a single voltage source in series with a single impedance connected across the two terminals A and B. We need to find the power loss across the 1 ohm resistor which is connected across the two terminals XY using Thevenin's theorem. So what we need to do is, I need to represent this entire network with a single voltage in series with a resistance, and then I need to find the power loss across 1 ohm resistor. So to find the Thevenin's voltage, what we do is we open circuit the two terminals across which I need to find Thevenin's voltage. So we need to find the voltage Vt across XY, and here I find that there is a current source. So let this be I. So this current source I divides itself into I1 and I2, right? So here we have I equals I1 plus I2. And what is I1? I1 is the voltage across the terminals divided by the resistance. Now what is the voltage across the terminal? It is Vt. Now since we have two parallel networks, the voltage across 5 ohm is Vt. The voltage across this combination 10 ohm in series with 10 volts is also Vt, right? So therefore I1 is equal to Vt minus, so this is in opposition with Vt, so I have minus 10 divided by R, V by R, plus Vt by R, which is 5, and this is 2 amperes. Okay, so let me multiply the entire equation by 10. So I get 20 equals Vt minus 10 plus 2 Vt, or taking this to LHS I get 30 equals 3 Vt, or V of t equals 30 by 3, which is equal to 10 volts. So therefore we have found out the voltage across the two terminals XY, the Thevenin's voltage, which is 10 volts. So now we need to find the resistance. So the resistance RT looking through the two terminals XY. So to find the resistance, what we need to do is, in the entire circuit, we need to replace the voltage source by a short, and we need to open circuit all the current sources. So when I open circuit, so this will not exist. I short the 10 volts, so I have 10 ohms in parallel with 5, and then I have XY, and I need to find RT. Okay, so RT is 10 and 5 connected in parallel, so RT is 10 into 5 divided by 10 plus 5, which is 15, so we get 3.3 ohms. So now the entire circuit can be replaced by a voltage source 10 in series with the resistance RT. So I have 10 volts plus minus, which is Vt, in series with RT, which is 3.3 ohms, and then I have 1 ohm across the two terminals X and Y. So we need to find the power loss across this 1 ohm resistor. So let's assume that there is current I flowing. So therefore we have 10 equals 3.3 into I plus 1 into I. So therefore I equals 10 by 4.3, which is 2.31 amperes. So the power dissipated across 1 ohm is I square into R, which is 2.31 square into R is 1. So we get 5.33 watts. Okay, so this is how we can apply Thevenin's theorem and find an equivalent voltage source connected in series with a resistance. In the next problem, we need to find the total internal resistance of the network looking through the open circuit through the terminals XY. Right? So in this circuit we have a dependent voltage source 5VL, and VL happens to be the voltage across the 3 ohm resistor. Now let us assume that V is the voltage across the two terminals XY, and let us consider the two currents in each of these loops. So let I1 be the current here and I2 be the current. The total voltage V is the drop across 1 ohm plus the drop across the dependent voltage source plus the drop across the 1 ohm resistor. So the total voltage V here in this loop is the drop across 1 ohm plus the drop across the dependent voltage source plus drop across this 1 ohm resistor. So V equals 1 into I1 plus 5 into VL plus 1 into I1 minus I2. So the current flowing here is I1 plus minus I2, that is I2 is flowing in the opposite direction. So V equals, so I have 2I1 minus I2 plus 5 times VL. Okay, now what is VL? VL is the voltage drop across this 3 ohm resistor. So therefore VL equals 3I2. So substituting this here, we get V equals 2I1 minus I2 plus 15 into I2. Right? So VL is 3I2, so 5 into 3 is 15I2. So I get 2I1 plus 14I2. So let me call this as equation 1. Now considering this loop here, so the total voltage, now considering the second loop, so writing KVL here, so this is plus minus, so the total drop in the entire second loop is 0. So let me consider the current flow from plus to minus as positive, whereas minus to plus is negative. So we have 2 into I2 plus 3 into I2 plus 1 into I2 minus I1 minus 5 VL equal to 0. So again VL equals 3I2, so let me substitute that here. So I get 2I2 plus 3I2 plus I2 minus 5 into 3 is 15 I2 minus I1 equals 0. So this is 6 minus 15, so which gives me minus 9I2 equals I1, or what is I2? I2 is minus 1 by 9 I1. So with a negative sign here. So let me substitute the value of I2 in equation 1. So let me call this as equation 2. So this is minus 1 by 9 I1. So I have V equals 2I1 plus 14 into minus 1 by 9 I1. So I2 is minus 1 by 9 I1. So we have V equals 18 I1 minus 14 I1 divided by 9. So which gives me 4 divided by 9 I1. Okay, so I want to know the resistance here. So the resistance here is nothing but V by I1, which is equal to 4 by 9. Okay, so V by I1 equals 4 by 9, which is approximately equal to 0.440. So this is the total internal resistance of the network looking through the open circuit, that is through the terminals X and Y. Okay, so like this we can use the Thevenin's theorem to find or to represent the entire active linear network with the two terminals AB, wherein we can replace it by a single voltage source in series with an impedance Z across. So in this problem we have not found out the Thevenin's voltage VT, but here we have used the concept of Thevenin's theorem to find the internal resistance through the open terminals XY, right? So make sure